Alrighty, in this video, we are going to be talking about number 5 and number 6. These are going to be dealing with, let's say, circles, I would say. Number 5, we have air being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. All right, so before I do anything, let's go ahead and draw my little sphere. And we know that volume increases at a rate of 100 centimeters cubed per second. So dV dt is equal to 100 centimeters cubed per second. Okay, and we want to know how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So we want to figure out what dr dt is, given that my diameter is 50, aka my radius is 25. Now, since we're talking about a sphere, remember that the formula of a sphere is 4/3 pi r cubed. And remember back in my little intro video, we have 4 pi r squared dr dt in terms of my derivative with respect to time. Okay, so we're increasing at a rate of 100 centimeters cubed per second. So I have 100 centimeters cubed per second is equal to 4 pi. Now we have our r, that's going to be 25 square. So this is going to be centimeters squared. And then we want to figure out what dr dt is. All right, so I'm going to go ahead and divide 4 pi 25 square centimeters square so that dr dt is isolated. If I do that, I'm going to have 4 pi 25 square centimeters square, and then I still have seconds. Notice how my units will cancel out so that I'm only left with a centimeter on top. And I have 100 over 4 pi 25 square centimeters per second, which is dr dt. And notice how I did not simplify it, so just call it a day and leave it like that. And notice how our units matches up, because if we're talking about the radius with respect to time, that's going to be centimeters per second. All right. So now what we're going to do, as I move all of this up, number 6, we have a pebble that's being dropped into a compound, causing ripples in the form of concentric circles. So we have circles among circles among circles among circles. And it tells us that the radius of the outer ripple is increasing at a constant rate of 1 feet per second. So if the radius is 4, at what rate is the total area of the disturbed water changing? All right, so we know that dr dt is 1 feet per second, and we know that r is going to be 4. Since we're talking about the total area, and this is a circle, we know that area is pi r squared. I'm going to take the derivative with respect to time, and then I'm going to plug in everything I know. So I have 2 pi, r is 4, but remember this is 4 feet, and then dr dt is 1 feet per second. And then if I simplify that, notice how my units should match up, because I have feet and feet, which is going to be feet square. So feet square per second, or 8 pi feet square per second. All right, in the next video, we will do number 7 and number 8. These are going to be problems where we are dealing with geometry.